Okay, welcome back. Now, this is actually a continuation from the part 4.5. Okay, uh, now we are going to look at the influence of stability derivatives on the longitudinal modes of motion. I'm not including this into my normal Tuesday lecture, but instead, this is also a part of once you try yourself dengan contoh case study yang sebelum ni, okay, dan kita boleh nampak clearly okay, apa influence bagi setiap derivative pada longitudinal motion, okay, pada Foucault and short period. Now let's look at the first stability derivative, which is MQ, the moment due to pitch rate plus moment due to the change of angle of attack. So this is the rate of change of angle of attack. Okay, so this is actually both are rate. So the moment due to rate. So the mode affected is the damping of a short period mode of motion. So ni kalau this is more banyak kaitan pada the possibly the size of the tail or the your location of center of gravity. Sama ada lebih dekat dengan neutral point atau lebih jauh dari neutral point. So increasing MQ and M alpha dot increases damping. And this is how these two are affecting the short period. Okay. But I guess this is more on the contribution of tail. Okay. So the larger your tail, the larger your MQ. MQ lagi besar. And it will increase the damping. Ya, betul lah. Sebab tail kat belakang tu kalau kita ubah dia punya attitude, okay, tail tu melawan. Okay. Dia melawan. So it increases the damping. So for M alpha, okay, moment this datang dari equation CM alpha, which is the slope of CM versus angle of attack. Okay, so this is how pitch moment changes with respect to angle of attack. So ini kalau kita tengok balik slope case yang dalam static stability, the slope is actually affected by the location of your center of gravity. Okay, the distance between center of gravity and the neutral point of the plane of the aircraft kan. So this one will affect the frequency. Okay, so lagi steep dia punya CM alpha punya slope, lagi besar dia punya frequency. Okay, lagi okay. So the steeper the slope, maknanya CG tu lebih jauh lagi daripada jauh ke depan berbanding dengan neutral point, the frequency lebih besar. Okay, so increasing M alpha of static stability increases the frequency. Okay, increase the frequency. So kalau CG kita move ke belakang dekat dengan neutral point, frequency of short period dia akan jadi rendah. Okay, the third one is XU. This is X force due to forward speed. Okay, mode affected is a damping of the Foucault or long period mode of motion. So if you look at this is actually sebenarnya related to the drag. Okay, aircraft yang drag dia besar, okay, CD dia besar, coefficient of drag dia besar, satu increase sikit pun forward speed pun dia punya drag akan naik banyak. So aircraft akan slow down lagi cepat. Okay, slow down lagi cepat. So this will in fact akan increase the damping of Foucault. Okay, so increasing the value of XU increases damping. Okay, increases the damping. So yalah, drag tu kan macam kalau kita model kan dia macam damping coefficient kan dashboard. Okay, dia akan lagi cepat. Okay, dia akan effect banyak pada Foucault punya damping ratio. Whereas ZU, okay, which is very much related to the lift, the change of Z force kan, lift force kan, with respect to the change of ini akan affect the frequency of full guide. So pesawat yang lift to drag ratio dia besar, naik sikit je ataupun turun sikit je dia punya forward speed, the lift akan naik atau turun dengan banyak. Okay, and this will affect the frequency. So ZU yang besar will increase the frequency of full guide. Okay, so how does it work? Okay, look at this. Ini adalah roots, okay, of these eigenvalues. Okay, so this is basically ini adalah real axis, ini adalah imaginary axis. Okay, ini kita punya pole. Okay, so ada two pairs of poles, one for phugoid, which happen at very close to the origin, another one is short period. Okay, so this shows actually bila dia dekat dengan ni, maknanya frekuensi dia rendah. Okay, undamped frekuensi dia rendah, and angle dia pun besar. Okay, angle dia kira dari sini kan, so angle dia besar, so damping ratio dia rendah. So ini long period, and ini short period. Okay, jauh, meaning that the natural frequency dia besar, undamped natural frequency dia pun besar. Okay, and the angle is less, meaning that the damping ratio dia besar. Okay, lebih besar. Now, the arrow ni yang ada kat sini, plot ni, nampak macam root locus ni, indicates the direction of decreasing static margin, ataupun maknanya center of gravity dia move ke belakang ataupun mendekati neutral point. So what happened? We look at the short period first. So bila dia mendekati neutral point, the roots dia akan makin pole dia akan makin turun ke bawah. Okay, dalam kata lain, bila center of gravity ni move ke belakang, the short period frequency itu makin rendah. Okay, sebab dia makin dekat kan, dia turun ke bawah tapi dia makin dekat. Okay, so bila ke belakang, frekuensinya makin rendah. Okay, makin rendah sebab dia kurang stabil, frekuensi makin rendah, tapi damping ratio dia makin besar. Okay, makin besar damping ratio dia. Okay, which is good. Okay, good lah, bad lah. Tapi kalau dia terlampau dekat, nanti dia jadi keras lah. Dia jadi overdamp. Okay, jadi overdamp. Dia jadi overdamp, dia akan satu pole akan ke kanan, satu pole ke kiri. And for phugoid, okay, so moving the center of gravity ke belakang will increase the damping ratio, which is good, but also decrease the frequency. Okay, lambat lah, respon dia lambat. Dia lambat nak habis, tapi damping ratio dia makin baik. Okay, makin baik. So CG ni kalau ke depan move jauh daripada neutral point tu tak best juga. Tak shock sebab dia punya damping ratio akan rendah. Both cases. Okay, both cases. Okay. Tapi kalau dekat sangat, nanti dia punya natural frequency makin rendah, tapi damping ratio nya bagus. Okay. That's one explanation. The second one is the effect of the tail size. Okay, tail size. So the direction of arrow shows if you increase the tail size, ke mana root ni akan pergi ataupun pole ni akan pergi. Okay. So let's look at the short period. So if you increase the tail area, okay, or kita jauhkan tail tu ke belakang, okay, jauhkan tail tu ke belakang, okay, meaning that your VH, tail volume ratio tu besar. Okay, so dia akan increase the natural frequency, tapi adakah dia akan increase dia punya damping ratio? Tak sangat. Okay, for short period root tak sangat, dia tak ubah damping ratio banyak. Okay, sebab dia cuma akan increase the natural frequency. Okay, sebab dia menjauh, tapi dia tak tukar sangat angle tu. Tapi for phugoid, dia akan menyebabkan phugoid punya damping ratio makin teruk atau makin rendah, sebab dia akan naik ke atas straight macam tu. So natural frequency dia improve, respon dia lebih cepat, tetapi damping ratio dia makin teruk kalau kita besarkan echo. So besarkan echo pun tak bagus tak semestinya bagus, jadi echo tu mesti ngam-ngam je. Faham? Ini case study kita dapat, case study kita. Alright, so next lecture nanti kita akan tengok the flying quality. Sebab sekarang ni dia tengok daripada sini, kita tak tahu mana bagus ke tak bagus. If you go back to the example, is this good? I don't know. Tak tahu. We have to look at the standard. Apa standard kita nak pakai, kita nak nilai flying quality pesawat tu. Dia bagus kat mana. Sekarang kita tahu apa yang derivatif ni buat pada pesawat. Kita dah tahu macam mana how to calculate. Tapi kita tak tahu yang mana bagus ke tak bagus. So apa standard dia. So yang itu rasanya kita tengok ke depan. Any question? Boleh tanya masa TBL atau tutorial time. Which is sejak lagi. Bila masa dalam minggu ni? Minggu depan pun boleh lah. Tak ada masalah. Anytime. Student. Selamat berpuasa. Thank you very much. See you again.